Welcome to Study Loop.
This is problem number 42 of chapter 23. In this problem, we're asked to draw a diagram of the situation, and this situation is a double slit experiment, so let's go ahead and draw the double slits. And the separation distance between these slits, we're going to denote it with the letter lowercase d. And the distance between the slit and the screen, we're going to denote that a distance L. Now let's go ahead and put the screen here. In this problem, the wavelength used is lambda equal to 630 nanometers. So let's go ahead and convert that to meters by multiplying it by 10 to the negative 9 meters for every 1 nanometer. So this becomes 630 times 10 to the negative 9 meters. The separation distance between the slits here is d equal to, well, we don't know that one, so that's going to be an unknown. We are given the length L, here it's 6 meters, and we are given the distance to the fourth bright fringe, 2.8 centimeters. So let's go ahead and convert that to meters. 10 to the negative 2 meters for every 1 centimeter. So this is 2.8 times 10 to the negative 2. And our units here are meters. Okay, so here this distance L must be much further than the separation distance, and we have the position of this fourth bright fringe. This is the position from the central maximum. So the central maximum is going to be given if we look at the center of the separation here. We draw a line from there to the screen. That's the central maximum. This y sub 4 is the distance from this central maximum to this position. So let's say that it's y4 somewhere up here. And now we can see an angle formed between this starting location and this y4. So let's go ahead and label this. This is going to be y4. And this distance is L, the separation distance. And then we see that the angle formed between the blue and green line is theta. So from the diagram, we see that tangent of theta is equal. So this is actually theta 4 because it's the fourth order bright fringe. This is going to be y4 over L. So let's go ahead and take the arctangent of both sides to see if small angle approximations are valid. So in degrees, let's see what this comes out to. This is going to be arctangent of y4 over L. So y4 is 2.8 times 10 to the negative 2 meters. And this is why we convert it to meters, so that when we put the 6.0 meters here in the denominator, the meters cancels out with meters. So let's plug this into the calculator. Let's see what we get. We get 0.267 approximately that, and we're going to save that onto the calculator in case we need it later. But that is a small angle, so this is going to be in degrees. Let me check the mode here. Yes, that's in degrees, so small angle approximations are valid. So this is approximately this much degrees. Okay, since small angle approximations are valid, let's go ahead and recall the formulas for Young's double slit experiment. We have d sine of theta. M is going to be equal to m lambda, where m is equal to 0, 1, 2, 3, 4, etc. Okay, we could solve this expression for sine of theta. Sine of theta m is equal to m lambda over d. Now, due to small angle approximations, we can say that sine of theta four is approximately equal to tangent of theta 4, and this is valid for small angles. So here we can say that this is going to be equal to y sub m over L. This is for small angle approximation. So in this problem, that would translate to, if we go ahead and substitute the part for sine, this is the part for sine. And here, let me put an approximate here for small angles. This is going to be approximately equal to tangent of theta, which is this. Let's go ahead and substitute the values here. This is going to be 4. Here for lambda, let's go ahead and substitute lambda. Lambda is this quantity. Y4 is this one, 2.8 times 10 to the negative 2. L is the 6.0 meters. Okay, and then we can solve this expression for D. So to do that, let's go ahead and take the reciprocal of both sides. So, you could simplify this with a calculator and then solve for D that way, or we could just go ahead and take the reciprocal here on both sides and then solve for D. So let's go ahead and take the reciprocal. So if we do that, we have this. D over this is going to be equal to the reciprocal here. So this is going to go into the denominator, and then in the numerator we have 6.0 meters over that quantity. And now all we have to do is multiply both sides by this denominator that's on the left hand side. So D is going to be equal to and let's go ahead and multiply that by this quantity. There we go. Meters cancels out with meters here, but then we have 1 meter remaining. So D comes out when this gets plugged in. Let's see what we get. We get 5.4 times 10 to the negative 4, and this is in meters. So let's convert this to millimeters. 10 to the 3 millimeters for every 1 meter. So then this comes out to be 0.54 millimeters. And that's going to be the separation distance between the slits here. Okay, so we've drawn the diagram. We've figured out the separation distance here, D. What else can we tell about these fringes? Let's see. We can say we're going to go ahead and use this formula. Let's go ahead and solve for ym. So since small angle approximations are valid, the distance d is much less than the separation capital L. So here let's go ahead and solve for y sub m. Y sub m then is going to be equal to m lambda capital L over d. And we know this by multiplying both sides by capital L. We are setting this equal just because small angle approximations are valid, so we could take the two to be the same. Let's evaluate y m plus 1. So if this is the mth bright fringe, this is the m plus 1 bright fringe. So this is going to be m plus 1 lambda capital L over d. If we want to find out the separation between two successive bright fringes, we could call this delta y, to be defined as y m plus 1 minus y sub m. So let's go ahead and plug these quantities in. Here, if we distribute the lambda L and D to the m, it's going to cancel out with this term, and all we're going to be left with is lambda L over D. So delta y, it's going to be equal to, let's go ahead and distribute here. Notice that we have a common denominator, so let's go ahead and distribute. Here in the numerator, we're going to have m lambda L plus lambda capital L minus m lambda L all over D because of the common denominator. Notice how this first term and the third term cancel out, and you're left with lambda L over D. So let's plug in the values since we know the wavelength, we know the separation between the slits and the screen, and we also know the slit separation, little d. So let's go ahead and plug in all these values. Here in the numerator, we're going to get 6.0 meters times 630 nanometers over the slit separation, 5.4 times 10 to the negative 4 meters. And this comes out to be 0.007 meters. So we're going to go ahead and multiply this by 10 to the third millimeters for every 1 meter. So meters cancels out with meters, and we're left with 7 millimeters. So that's going to be the separation between each successive bright fringe. So let's go back up top here. Let's go back up top here. The distance, the separation between Y4 and Y3 is going to be 7 millimeters. The separation between Y3 and Y2 is going to be 7 millimeters, and so forth. So Y4 and Y5, if we have another bright fringe somewhere up here, the separation here, Y5 and Y4, is going to be 7 millimeters. And that's what we get about that interference pattern on the screen. So here, actually, let me change this because that's not right. This is right. Okay, so yes, that separation delta y is equal to 7 millimeters there. So this concludes problem 42.